Good morning, students. Again, we are back to our course Power Generation Economics E704C, and this is our lecture number 7. And we were discussing about the thermal unit constants, that is minimum uptime, minimum downtime, and crew constants. We have discussed about the minimum uptime. So, immediately when the unit has been started up, it should not be shut down. So, there is a minimum uptime for the generator to operate, let it be 8 hours or 10 hours or 12 hours. So that minimum time uptime the generator must be on, that must be maintained. So this is the minimum uptime. And similarly, minimum downtime, so if the unit is off for a certain stage, so immediately we can't start it. Suppose it has been another down stage for the last half an hour, and we are starting it immediately for our satisfaction of our load. So, and this is required. So that is not feasible. We should not start down if it is shut down for a small amount of time. So if there is a minimum downtime, maybe a downtime of 10 hours, so we have to maintain it. So after 10 hours, it can be thought that it should be operated or not. Similarly, crew constants are there. So suppose there are 3 generators and our crews are suppose 5 number of crews are there. So we can't operate all the 3 generators at a time, because crews are the persons who will be seeing whether the units are in the proper condition or not. So if for the first generator or any number of generators, 4 numbers of crews are required, minimum 4 numbers of crews are required for each unit. So 5 crews can satisfy only 1 generator. So these are the all sorts of constants for the thermal power plant, and we have to see. Now next topic is about our startup cost. Startup cost is, write down, the startup cost vary from a maximum cold start value, maximum cold start. So you remember this term, maximum cold start value, to a very small value if the unit was only turned off recently and it is still relatively close to the operating temperature. So that means, suppose the unit 1 has been shut down for a certain period of time, and it has just completed its minimum downtime. Suppose the minimum downtime is 8 hours and it has just completed 8 hours of time, just complete, and the operator thinks stop starting up here. So it has a cold start value to a minimum to a very close of the starting of the thermal unit. So here is your cold start. The cold start value is here, and this much time is 8 hours and it can be operated. So if the unit is, the minimum downtime is 8 hours and we are operating it after 3 months, so the cold start value is very much less and we have to give some energy to the unit so that it can be started off. So that is the meaning of the cold start. So the cold start value, if it is less, so immediately we can start. If the cold start value is very in the not to the operating point, of the starting, if it is has been shut down for 3 months, the minimum downtime is 8 hours and it has been shut down for 3 months, the cold start value has been to a very less value. It is not close to the operating point. So we have to see the first approach of cooling allows the unit boiler to cool down and then heat back up to a operating temperature in time for a scheduled turn on. So another approach is that it requires sufficient energy be input to the boiler to just maintain the operating temperature. Now the next constraint is our hydro constraints. As students, we have discussed that there may be a mixture of hydro and thermal power plant. So for the unit comment solutions, so you have discussed there are lots of constraints, that is your ramp up constraint, ramp up, ramp down, start up, shut down, all these constraints, security constraints, security constraints, under security constraint there are also lots of constraints. One is your reserve constraints, reserves, that is your comes under spinning reserve constraints, SPINNING, spinning reserve, and there are other constraints, line loadability, voltage constraints, reactive power constraints. So all these constraints we have to see: ramp up, ramp down, start up, shut down, security constraints, power balance constraints. So all these constraints we have to see, and out of that the hydro constraints is also. So all of you know that the base load is for the nuclear power plant, for the base load, and for the peak load we use hydro power plants. And in between thermal power plants are being used. For the peak load we use hydro power plants. For the base load we use nuclear power plants, and thermal power plants are cheap available, coal is available. So mostly throughout the world 60% of our generators are thermal power plants. So these are the constraints. Now 5 units are there, which unit are to be started up. You have to satisfy all the constraints. There is a cost constraint, and the main constraint I have not told, that is your cost constraint. We have to satisfy the minimize the total cost, that is our objective function. Minimize the total cost, that is our subject to the constraints: ramp up, ramp down, start up, thermal constraint, security constraint, power balance constraint, reserve constraint, line loadability constraint, voltage constraints, reactive power constraints. All these things we have to take into account, and we have to solve by dynamic programming method or branch and bound algorithm, or through MATLAB also. There is one program that is INT-LIN-PROG, means integer linear programming, and all these things are you see, these are not non-linear functions, these are linear functions subject to the cost. These are the linear functions, and though it is non-linear, if we apply this function integer linear programming through MATLAB, we have to make a non-linear function to a linear function, just as our Newton-Raphson and Gauss-Seidel are non-linear functions, but DC load flow is a linear function. So we have to change for the approximation part, we have to change to the DC approximation, and we have to solve by integer linear programming methods, where the values will be either 0 or 1. That is your last class we have discussed that it may be a binary programming method. So we are discussing about the hydro constraints. So the hydro, the fuel is the water that is cheaply, abundantly available. So if it is a mixture of thermal and hydro, we have to use 2 hydro or 5 thermal, and which time that we have to use the 1 hydro and 1 thermal. So that is the mixture that becomes a little bit tougher problem. So write down, the hydro scheduling will be separated from the unit commitment problem. Operation of a system having both hydro and thermal power plants is, however, more complex, as hydro plants have negligible operation costs but are required to operate under constraints of water availability for the hydro generation in a given period of time. So only what is the constraint for the hydro? Hydro is the availability of the water. In the thermal power plants, the constraints are, these are the things. Even crew constraints is also there for, and for the hydro, the only is that the availability of the water, whether the water is available or not. So another constraint is must run. So if there are 5 units in a power plant or 6 units in a power plant, let the 5th unit must run always. Now why it will be running all the time? Now it is the for the keeping the voltage constant. For the there should not be an imbalance in the voltage. So I write down, for a must run organization to some units of the plant during certain events of the year, maybe during the peak load time, which yield the voltage support on the transmission network. So due to the voltage support, there must be a must run units always during the certain period of time. This unit must always run. Let the 5th unit must always be running during a certain period of time, this much. Why this must run? This because to keep the voltage constant in the transmission system. So another constraint is fuel constraints. So if in a thermal power plant, which fuel is cheaply available, availability of the fuel, so that is also another constraint. So what you have learned, hydro constraints, must run constraint, must run, M-U-S-T, must run constraint, hydro constraints, hydro constraints, must run constraints, and number 3 is fuel constraints, fuel constraints. So all these things you have to keep in mind. So which fuel is cheaply available, what is the distance from the power plant, so this fuel is available, so the cost may increase due to the transportation. So that things also we have to keep in mind. So there are some methods of solving the problems. So unit commitment solution method, one method mostly that we have been using, that is DP method, that is dynamic programming solution method. Another is very uncommon method, that is priority list method, priority list. Now under priority list method, and another one is Lagrange relaxation method. So these are the methods, and through the softwares we can use the MATLAB programming, that is binary integer programming. Another one we have told, that is int lin prob. The function is int lin prob program. So this one also we can apply, and we have to fit the data we can solve, and this also satisfies. This program has come from the branch and bound algorithm, dynamic programming. This is a very standard method, and these are also the priority. Now if we think that this generator is more prior to that, this is to be operated. So we have to think. And Lagrange relaxation, this is also another mathematical technique we have to apply, but this is not necessary for your course method. You have to know the names of the methods. So another thing, let us tell that throughout the time period, our load is somewhat like this. Suppose this is your 1400 megawatt, this is your 600 megawatt, this is 4 p.m., this is your also 4 p.m., 4 p.m. to 4 p.m., 24 hours, and this comes about your 4 a.m., 12 hours and 12 hours. So these are the points where the units to be shut down, units to be shut down. And here start up, here the units are to be started up. You can see that the load is decreasing. You can see that the load is decreasing, so units must be shut down. And here the load is increasing, so units must be start up. This is start up. Rather, you can say start up, and this one is shut down. Now, if our 3 units are like this, the cost function of the 3 units, if it is given like this, 0.002842 Pg1 for the first Pg1 square plus 8.46 Pg1 plus 600, and the cost function of the second unit, 3 units are there, 0.002936 Pg2 square plus 8.32 Pg2 plus 420. So all these are in rupees per hour. And the cost function for the third unit, 3 units are there, 1 number, 2 number, and the 3 units are there, and the cost function of the third unit is 0.0064464449 Pg3 square plus 9.884 Pg3 plus 110 rupees per hour. So these are the schemes. Cost functions are given. So one scheme is that enumeration scheme. So write down, enumeration scheme is that a straightforward but highly time consuming way of finding the most economical combination of units to meet a particular load demand is to try all possible combinations of units that can supply the load. This load is divided optimally among the units of each combination by the use of coordination equations so as to find the most economical cost of the combination. Then the combination that has the least operating cost among all these are determined. Suppose the load is 600 megawatts. Suppose the load is 600 megawatts. So you have to see how many possible combinations. 3 units are there. 2 to the power 3 minus 1, that is 7 combinations are there. So we can make one chart like this. We can make one chart like this. Unit 1, Unit 2, Unit 3. 3 units are there. Unit 1, 2, 3. And their PG maximum and PG minimum, and how much the loads they will satisfy, PG1, PG2 and PG3, how much many amount of loads and their cost functions. So suppose all the 3 units, this is a time consuming, all the 3 units if it is off, that means the system is not working. So the second one is that we will make the third unit off, third unit on rather. If we make the third unit on, so what is the maximum of the third unit? It is 300. You see from the, so maximum and minimum constraints are also given. So the first unit has the minimum of for the first unit 200 is less than PG1 is less than or equal to 650. For the second unit it is in between, 150 is less than PG2 is less than or equal to 450. And for the third unit, here I am writing, and for the third unit it is 300. Now 100 is minimum, is PG3 is less than 300. So that's why I have written here 300, and it is because I am making it on the third unit, and the minimum and the this one is this one. But our load, what is our load? Load is, I think it is 600. If this one, so can it satisfy? It has a maximum of 300 units. It is a capacity of 300, but the load is 600 megawatt. So it can't satisfy. So this is infeasible. So this is infeasible. This is infeasible. So this combination is not satisfied. So this, let us make it off, on, off. Now this one, this is also infeasible. This is also infeasible. Why? The second unit has a maximum capacity of 450, but our load is 600. So this one, so what is the 150? Maximum is how much? 450, and this one is 150. So this is also infeasible. So this combination gets cut, this combination gets cut, and now this one. If this is on, this is on, and the first one is off. Now you have to see whether this combination is feasible or not. So what is that maximum load? 750. Second and third, you see, second and third. So 450 plus 300, 750, and the minimum is 150 and 100, 250. So within this range, 600 is, so this is feasible. This is feasible. This is feasible. This is feasible. And what is the total cost we will be getting? You will be getting of a total cost of C2. So the cost for the second generator. What is the cost for the second generator and what is the cost for the third generator? So this one will be, so under coordination equation, you will be getting 450 and 150. So 2 and 3, 450, this becomes 450 and 150. 450 plus 150 is 600. And what is the cost? You will be seeing. And you satisfy, you get the cost. Similarly, all the combinations you have to see. And you will be seeing that if all the three generators are kept on, the total cost becomes 4858. 4858. The total cost becomes 4858. And out of many combinations, this cost is minimum. That means if the three units are kept on, this cost is minimum. So, but is it for the unit commitment? I can operate, there are three units, I have to operate all the three because my cost is minimum. But this is also not feasible. Why? Because you write down the least expensive was not to supply the generation with the three units running or even any combination involving two units. So I can't take 2 units at a time or 3 units at a time. Rather, the optimum commitment is to run only unit 1. You have to see that if I run only one unit, the first unit, because you see my load is 600 and it satisfies, first unit operates, the maximum load is also, this is feasible. If I run only the one unit, this is feasible. But this cost is more than this cost. If I operate all the 3 units, the cost, but this is not feasible in unit commitment. The most economic unit was to run only unit 1, the most economic unit, because the load can be supplied by that unit operating closer to the best efficiency. So the unit 1 itself can operate at the best efficiency. If the 2 units or 3 units are operated, the efficiency point, the operating point of the efficiency will change. It will go to some other points. So you write down the operating unit is closer to its best efficiency if unit 1 is operated, and both unit 1 and the other unit will be loaded further from their best efficiency points. So from the best efficiency points, if I operate maybe 2 and 3 or 1 and 2, though the cost is minimum, so the efficiency operating point will be changing. So it is most economical under unit commitment to operate this unit, because this satisfies the load and the efficiency will be maximum. Though the cost, if I run all the 3 units, cost is minimum, but still I have to operate the first unit because the efficiency will be maximum. So students, again we will be meeting to our next lecture. Thank you for your listening, and go through all the courses, learn, and any sort of doubts you have, you can discuss with me, you can ring me up. Thank you very much.